nice full house. That's what we like to see. So I'm Greg Law, co-founder of Undo.io. I'm joined by Chris, Senior Solutions Architect, and we're going to talk to you about GDB. Because debugging is hard. I think it's a well-known quote by Kernighan that debugging is twice as hard as writing the code in the first place. So if you're as smart as you can be when you write the code, you are by definition not clever enough to debug it. Well, I think that's a good quote. I think what he means by that really is keep it simple when you write the code. But I think there's an interesting corollary to that, which is that debuggability is like the limiting factor on how good we can make the software. Right? As humans, we write software to be at the level, at the edge of our ability to comprehend it, and usually just beyond, right? So debugging, I think, completely dominates software development. I don't think we talk about it nearly enough. There's lots of tools out there. We only have 1 hour, so we're just going to cover some very small parts of just one tool, GDB, which I'm going to assume that everybody, well, no, I don't need to assume, let's have a show of hands. So who has used GDB like ever? Pretty much everybody. Good, that's what I was hoping for. Who's used it in the last 2 months? Okay, in the last month? Okay, this is what I can usually see. So we've kind of got a skewed sample here, right? We've got people who are like you are, by definition, interested in the topic because you've come to this talk. But it's not something that people get out all the time. It tends to be a bit of a tool of last resort. There is a lot to it, a lot of depth. The idea of this talk is not that you come away being an expert and like knowing how to do all this stuff. It's not a tutorial. Firm believer in you only really learn something when you do it. But hopefully there's a lot that you just probably don't know is there. Right? It is I learn something new. Every time I give this talk or one of these talks, I learn something new. I just learned something new this morning when we were practicing with Chris, and he showed me something that I didn't even know you could do, which he'll show you with Python Interactive in a moment. So yeah, I learn something new every time. The point of this is to just a bit of a smorgasbord, get it out there, you hear about it, and then when you need it, maybe in a month's time, maybe in a year's time, hopefully you'll think, oh yeah, that was that thing I saw. Maybe I can look it up on the documentation. Right? So it's just a bunch of stuff, but you have to, the trouble with these tools is, GDB is probably quite extreme in this regard. The documentation's pretty good, actually. It's pretty comprehensive, makes sense, it has good examples, but only if you know it's there, right? You can only kind of use the documentation if you know what to search for. Well, you can Google it, but again, only if you know it exists. So this is just going to get the stuff out there, you're going to kind of know it exists, and then you can hopefully look it up. So I'd like to distinguish between easy to use and easy to learn. And GDB is definitely not easy to learn, but it is quite easy to use once you know what you're doing. It can be actually very effective way of finding out what your code is doing. And I often start my talks with, I think GUI Mode actually is becoming more well known, but I think it still wins the prize for that combination of least well known and most useful. So maybe do another show of hands. Who has used GUI Mode on GDB? Okay, maybe half, okay. Who uses it as their default thing? Use it all oh wow, hardly anybody. Okay, interesting. I always use it. I just think it's the best way around. Of course, you can be using GDB from within Emacs or from within CLine or VS Code or something, and then maybe you don't need it. But often we're SSHing onto a box or something like that, and we don't have the luxury of the graphical interface. So let's go a very quick tour through GUI Mode, text user interface. So here's the classic. Let's compile it. I like to compile with -G3 because that gives a slightly better debug experience, although it won't make any difference on this tiny program. We run it load it up into GDB. Start. So here we are. So this is what's called, this is a text user interface really, isn't it? But it's the CLI, command line interface. And we can get into GUI mode in a number of different ways. We could actually just start GDB-TUI, but obviously I haven't done that here. I can go, probably the easiest one is I can just go layout source. So choose the different layouts, and there we are. Got my cursors, GUI mode, and I get that context. So I can see what the program is doing. And I can go back with, is it layout CLI? No, how do I go back? layout prev. No? See? And I learn what I don't know. But I can go back with Control XA, that does work. So Control XA will toggle between TUI mode and CLI mode. If I'm going to just start that again. Right. Because I wanted to show you something else. So that's Control XA, or layout source. Going to go Control X2, I get to look at the assembly code, which is sometimes useful. And if I go Control X2 again, I get kind of both. Why don't I have any?
You haven't started.
I have started. I don't know. Anyway, whatever. So now I've got the assembly, disassembly here, and the source code at the top. So that's kind of useful. I can actually cycle through this again, Control X2, and I'll get to see the registers. Why is it telling me registers are unavailable? I don't know, because like clearly they're there. Whatever. That's usually better. Anyway, let's go back to the. That's usually that's what I spend most of my time in when I'm in GDB. We can one of the things that if you're in TUI mode, again, this is the easy to use, hard to learn. Often, so let's get a backtrace, for example. Often with GDB, we'll do up and down arrows to get through the command history, right? But when I go up and down arrows, I just move that window up and down. So there's a number of things I can do here. I can go Control P for previous command and Control N for next, which is kind of the standard kind of GNU binding, read line bindings. Or I can go, this is something I learned the last time I gave this talk, focus command, and that will put the focus in the command window. Now, up arrow and down arrow do what they always did. So that's kind of cool. What else can we say? I think that's most of what I wanted to talk about. And Control L to refresh the screen. So TUI mode often goes horribly wrong. I mean, sometimes kind of by design. So I'm running the inferior, the debuggy, inside the debugger, so they're sharing a terminal. So when I'm about to type next, when I type next, it's going to execute that printf, and it's going to draw all over my nice TUI window, right? So, well, didn't do quite what I was expecting, but it's a bit of a mess. Like, I don't know what's going on here. I'll go over on the right, but Control L, and everything is redrawn. So you will need that quite a lot. It usually works. Sometimes that's not quite enough, and you have to come out of TUI mode and back into TUI mode. But most of the time, it kind of does what you need and what you want. All right. Chris, Python.
Yeah, so I'm going to talk about Python. And unfortunately, I have to use this mic, which is going to make typing a lot more fun. Or Greg's going to have to do
I'll do the
stand.
TV thing, yeah.
See, I have a mic stand now. So, yes, we have Python, fully available, integrated. I'm now slightly worried that Greg's pointing a microphone at my face.
I want to get the on there.
Yeah, get it on the screen. So let's just start this quickly. GDB, hello, all we've got to use hello world type thing. So let's just do a start. And, oh, look, slightly more adventurous. Hello, meeting C++ 2022.
Oh, you've prepared.
Look at this. It's almost like I knew I was coming. Okay, so we have Python here. So people like Python print. Hello, everyone. Wonderful. As we saw on the slide, I will reach it. Oh. That one. Yeah. Just on the side, we also have the interactive mode. So single commands you've just seen me do. Actually, that's great, but sometimes you want to do something a bit more complicated. So you can just start the Python line, and then you get multi-line Python. So print. Oh.
Uh-oh.
There you go. Print multi-line. Print. And with Control D, as you might be familiar, and then Control D exits and executes the entire set you've got there. And then as we saw on the slide, I'm not going to go back to that because I'll just get confused again. So we can do the Python interactive. At this point, we're now in interactive Python. Note the prompt's different. Instead of 1, we've got 3. So now I can do print. Patient. We want to get our printing and our access done immediately. So this is allowing us to do standard Python things there. Everything's available to us that you'd expect with Python, so you can go out to the outside world, you can bring all sorts of modules in here. If if I go back to the slides now, and we go to the next slide. Sorry, first, we can also source Python scripts, and you'll see me doing that in a little bit. We also have access to GDB. So we've got the full interpreter there, everything in Python, but we also have a GDB module we can use. So let's go back. I'll Control D to get out of that again. So let's say we want to do Python gdb.execute list. And you might think, well, that's kind of pointless because I could have just typed list. Obviously, it's continuing the list, so it's not doing the same thing. But if you've got a complex Python function, you can use this to access the state of what's going on, execute commands, even navigate. So you can have your Python scripts modifying code, continuing, setting new breakpoints, and all sorts of dynamic and funky stuff. I'll let you figure out what you want to do there. So that's that, but there's also things like printing the program counter. So I can print that. Again, with Python, I can print parse and eval.
You've got an extra quote there.
Okay, good. And we can access this data. So we're able to access expressions as well from GDB. All of this is accessible to your Python code, so you can do all sorts of funky things. Obviously, as I say, you're not going to be doing this interactively the way I've just demonstrated it. This is for integrating into scripts and doing more funky things later, but hopefully this gives you just the basic understanding of what's there. Let's go back to the slides. Custom prompts. So you can see you can just set the prompt in GDB, so set prompt. So by default we have GDB. Why would you want to do this? Well, for my colleagues and I, we spend a lot of time debugging GDB itself. So you might want to have one window which is clearly the GDB that you're debugging, and another window which is clearly the GDB that's debugging it. More realistically, for people in more normal use cases, you might have like a client-server session, maybe remote debugging on two separate hosts. You might want to label one as client and one as server, so you know exactly which session you're in when you're trying to debug multiple processes that can't be easily managed under the same thing, although Greg will show you ways to do multiprocess debugging later. But you can also use Python, and you can see here we're using the hook prompt, so rather than looking at slideware, let me quit this and do GDB. So this is an example program. I'll start it. You can see we've got a GDB prompt, but if I source prompt.py, we've now got a more interesting prompt. We've got the time of day. I can start stepping, and you can see we've got the frame that we're in. Details of where we are as I step through this very simple code. It's not doing anything really interesting. This is purely showing just as we're stepping on, we can do interactive things with our prompt to get useful information there. Again, this can provide all sorts of value. Maybe you're wanting to track specific users, or you've got a whole load of transactions in flight. You need to remind yourself what one you're working on. Other metadata you might want to pull out of the state of your system and have it at the prompt for you so you can see what you're doing. It's an alternative way of displaying things rather than having like the display feature that we'll talk about later briefly to output things every time you stop. This is just there all the time and constantly updating. Which also can help if you've got multiple processes running. Maybe you've got multiple threads running and some of them in a non-stop state. You can keep track of your memory usage. Maybe you want to put that there. All sorts of things. So that's great. I've shown you how to do it. Let's actually have a look at how this is done. So now, what we did find, we did a little trial of this earlier, and you can't read all of that. So let's take off the syntax cornering. So we've imported GDB. This is going to be needed, you can see within the GDB select frame. So this is how we got the function name we're in. Also using time, so we can get the time of day. Basically, we have a function, my prompt hook, and we're going to associate that with GDB prompt hook. So this is how you register for events. So every time the prompt is being displayed, it's going to call this, and this is going to work out what the current time is, find out what the frame is, and display that data in the prompt. So that's the string. There we go. That. So very basic, simple way of doing that. Let's go back to slides.
I think what might just be worth saying.
Sorry.
So I'm guessing for most people they're happy with the regular GDB prompt, but I think that's a really nice demo of just the kinds of things you can do, right? This is just not like, hey, Python and GDB is cool because you can change the prompt. Python GDB is cool because you can, if you can imagine it, you can probably do it, right? And you can hook right into GDB and sort of change its behavior in whatever mad way that you want to.
Okay, you're doing a wonderful mic stand job.
Yeah,
I think everyone can hear me clearly.
I found my vocation.
Yeah. Okay, so another use of Python is pretty printers. Now, most of you have probably come across pretty printers for the standard library pretty printers. You may not necessarily have an understanding of how they work or what's going on behind the scenes, but they're basically Python, that's like this. On the slides, you can see there's an init and a toString. So when you're printing a certain type, once it's hooked up with, frankly, the boilerplate at the bottom, so anytime a mystruct is printed, it's going to call this. It'll do the toString, and this allows you to do some funky printing options. So if I come back here, let's go over to here and quit and GDB. Quickly on this one. Start. So we've got an example here where we've got this value t. Also, just scroll up. You can see it's got two elements, and we can see I've got a good, a bad, and an ugly, or maybe a good, a no canary, and a bad canary. I might have to rename them. Let's just advance to line 24. So these have now been initialized. I can print. No, there is no God. What a shame. we can be good, and we can see that's sort of great. It's very raw standard data structure. I can be bad, and it's like those decimal numbers, they're not pretty clear what's going on, and fundamentally this is very raw. If I source value .py, and I try that again, let's go back to pgood, we've now got just the data and everything's happy. You think, well, okay, well, you've hidden things you don't really care about. So that's often the case. You've got data structures that have a whole load of stuff that isn't necessarily critically important to the way you're working. Some of it's just how your system is glued together. Let's look at the pbad. See, now we've been able to identify that it's bad, so we're providing metadata analysis of the variable as well. So this can be extra helpful. I can do the p, no canary, and again, uninitialized data. This is very straightforward. I'll try it. Let's just very quickly. I'm not going to go through the details. I will turn the fonts off so you can actually see the text. So again, we have the toString function. We're accessing the values, and we're checking, have we got the good value, output data, is it corrupt? Show that it's corrupt and output the full content, and if it's uninitialized, output that. So the idea being you can do pretty much anything you want, and you can see it again at the bottom, we have pretty much the same 4 lines of boilerplate, which in this instance is associating the value t type. Okay, so that's a quick example. I've got another quick one. You think we've got time to do some?
Go on then, yeah, very quickly.
Let's go for it. Why not? What have we got to lose?
Time.
That's okay. You're doing a great job there. I'm not having to hold that heavy microphone.
My arm's getting tired. Yeah.
Okay. Let's come out here. Another example. GDB squares. Start. So here we have a slightly more complicated data structure. It's a linked list. That should be reasonably obvious to people. So we've got the pointer to the next element and the number and squares. And we've got a bit of code which is just going to populate like 10 entries of that. So again, let's advance to line 22. And I can p star squares. We can see the first element. So that again. So the second element. Actually, this is getting a bit cramped. Win, height, source, 8. I don't care about the source code. I want to show you what I'm typing here. So an extra bit of TUI for you. You can change the height of the source window. So yeah, as I say, I can do this. I can go back up. I can go again. And we can follow it down. That's not great. Let's look at a slightly more complicated pretty printer. This one is designed for this particular linked list. So if I go back to what I did before, so the first one, we're printing, we've got a squares list, we're actually iterating down the list, finding all the entries, and displaying it here as a map. I can still do what I did before, you know, it doesn't change any of the way the expressions are evaluated, so if I do that, we'll see just the last 8 values rather than the full 10. So everything is still working, the printing is happening once the expression has been evaluated, if that's not clear. Let's have a look at how this is done. I'm not going to explain it in great detail for time, but I will again fix the fonts. The toString, again, the children allows you to do more complicated structures, so it allows you to look at it, and then finally the display hint map says it's a map, one value to another. So you've got this, I'm sure it's recorded, and we'll be happy to help you understand this stuff from that, but there's plenty of documentation on Pretty Printers, lots of stuff out there, and they can get far more complicated than this if you want to. You can do things like CRC checking a data structure, for example. If you've got a CRC in it, why not check it and validate it and answer whether the data structure is bad or not when you're printing. All sorts of things you can do when you have access.
Thank you, Chris. Let's do another show of hands. Who uses Pretty Printers with GDB? Oh, not many. A couple. Mm-hmm. All right. So sorry? For STL. Oh, that's cheating. But yeah, so STL comes with, so if you're using STL, there's usually Pretty Printers like in the distro to help you do that. I'm going to make a promise to you. If you, I just lost, it's a bit awkward. Right. If you write some Pretty Printers, your future self will thank you. You'll be glad you did. They're a bit of a pain. You can see here, you know, it is unfortunate that you need quite so much boilerplate. I'm not quite convinced you do. I always expect somebody's going to tell me you don't need that much boilerplate, but as far as I can figure out, you do. Whatever. We all know how to copy-paste. It is a significant quality of life enhancement, I think, if you write Pretty Printers for your main data structures. Okay, right. GDB init. Not going to see too much on this one, but here's some. I think try to keep it simple. I have had several occasions now of customers saying, oh, your tool doesn't work, and we try and figure out what's going on, and they've got things like, I've seen this more than once, a run command in their GDB init, and that just makes life really hard. I think don't do that. But these are some useful things. So set history save on. So this is, so when you're doing that up arrow to get your command history, you can, we'll remember it across GDB sessions, which is very useful. Pretty printing, pagination, whatever. I really wouldn't put too much more in your GDB init. Just source what you need to. Also, though, which GDB init? Well, annoyingly, we can have several. So you can have a GDB init, .gdb init in your current working directory from which you launched GDB. You can have a .gdb init in your home directory, which obviously is going to. There we are, look at that. So I completely lied. I've got more stuff than that in my GDB init. But you can have GDB init in your home directory, which obviously will apply to any GDB you start from whichever directory. And there's also a system GDB init, which depends on your distro, depends on the way that GDB was built. But if you go man GDB, it will at least tell you. So somewhere.
I think it's also in the bottom of GDB-help.
Is it? Let's do that then. That's what I was trying to think of, maybe. Yeah, right. So there we go. So on Ubuntu, it's built such that you've got a system-wide GDB in, etc., and in etc., and it will do these GDB inits in an order, and I forget which one it is. I'm sure the documentation would tell us. So there we go. Right. Remote debugging. You want to show us one very quickly? Yeah. If we leave the mic there, what happens? Does it pick you up?
Is this picking me up on the microphone?
If I move away.
Okay, if that's working, hopefully you can hear me. So for remote debugging, as we saw on the slide, there's basically a very simple tool called GDB Server. So I've got two windows here. I'm going to set GDB Server up to run on local port 2000, and I'm going to run my hello function. So that's up there. I'll turn it back. This isn't good. Let's make sure we can see it. We'll crunch the text, but we'll be able to see what's going on. So on this side, I'll launch GDB, and now I do target, remote, local, host, 2000. And so this is now going to connect GDB to this GDB server. You can see on the right side, we've got connection. We're at the very start of the application. It is actually running, but we're at the start of it. So let's just set a temporary breakpoint at main, and we'll continue to main. So at our source code, I could do this. It's sufficiently small, you can sort of see what's going on. But fundamentally, all I'm going to do is hit next, and we can see it's outputted. So we can do this debugging. In this instance, it's on the local host, but it's just an IP address. You can do this wherever you need to. So certainly that example I mentioned before, where you have a client and a server type thing where you're trying to debug both sides, this is quite possibly a way you'll be connecting to one of those targets to do that. Certainly allows you to keep things efficiently on your side. I think that's pretty much it from that one.
Right, what's next? Yes, breakpoints. Okay, so we all know about breakpoints, so I'm not going to ask for a show of hands. I'm sure everyone's done breakpoints. But there are lots of breakpoints, lots of different types of breakpoints. So break food, that's our normal kind of breakpoint. T-break, I only figured out relatively recently. I don't know if this is a deliberate pun, but I like it. So T-break, I encourage, like all good Englishmen, we should all take a tea-break. But a temporary breakpoint, so yeah, you set the breakpoint, you run, as soon as the breakpoint is hit, it will then be removed, deleted.
It's not just that, it's proof that GDB was written by an Englishman, because when you start in GDB, you set a T-break, so you start with a T-break.
Our break is a regular expression breakpoint. So this allows you just to, rather than a line number or a symbol to break on, you can give a regular expression, and any function name that matches that regular expression will get a breakpoint set on it. So if you're not careful, you can set thousands of breakpoints kind of by mistake, but that can be very useful. Maybe I've got a common prefix of a sort of module and I want to put a breakpoint on all of them. I can do that easily with our break. Thread-specific breakpoints. Should note that if you do a thread-specific breakpoint, like we've done here, break foo thread 3, all threads will stop when they hit that breakpoint, but GDB will silently continue them if they're not the thread that we're interested in. This is not the thread we're looking for. Conditional breakpoints, you can so you can have pretty much any expression following the breakpoint, and then it will only, again, GDB, again, the program will stop every time it hits the breakpoint. GDB will evaluate it. However, if you're doing remote debugging, you can configure, and your remote debug server, your GDB server, is capable, you can get it to do the evaluation of the expression in the server, which stops it pinging back to the host, evaluating some expression, probably fetching lots of data. That could take a really long time, depending on the latency of your connection of your remote debugging. So you can do agent breakpoint evaluation if your GDB server is up to it. The default GDB server is. We can delete them, we can disable and enable them. And we can just type disable on its own, and that will disable all breakpoints and watchpoints and catchpoints. Talking of which, so then we have watchpoints. My formatting's a bit broken, never mind. Right, so we've got regular watch. Now, watchpoints are, I think anyway, a bit confusing until you've figured out quite how they work. So we're watching an expression, right? If GDB can, it will use hardware assistance. It will program the CPU to stop when the watched data is actually modified. So before barreling on, who uses watchpoints? Show of hands. Oh, it's more niche than I thought. Okay, right. So watchpoint, sometimes it's called a data breakpoint. That's what it's called in Microsoft land, right? So we've set up watchpoint, we're going to run, and GDB will stop when the watched data changes. Two broad types, hardware and software watchpoints. Hardware watchpoints are almost certainly what you want because the program runs at basically full speed as long as the CPU supports it. They are limited in number, like x86 only supports 4. I think ARM64 will support 64 or 16 maybe. But that's usually enough, right? If you're unlucky and you get a software watchpoint, GDB will single step your program one machine instruction at a time and evaluate that expression between every single step and stop when it changes. So that will run like super slowly. And if you're not careful, you can end up it's really easy to end up with a software watch point by mistake, because like it doesn't tell you. Let me show you. So what have we got here? What's suitable? I think structs will do. So here's a program. So I can watch X like that. That will put a watch point on X. But notice subtly the difference here between watch X. X is a structure, right? And it's a big-ish structure. If I watch X.A, hardware watch point, right? So it's really easy to miss. It's sort of historical. It's because GDB had support for these watch points before mostly there was hardware support for them. So then hardware watch points got added later. So if GDB can, it will use a hardware watch point, which, as I say, is what you want. It will evaluate the expression entirely. So if I go like watch foo points to bar points to baz, it will stop whenever the value of that expression changes, which isn't quite the same as stopping every time the data that any of that memory is written to, because they might be written to with the same value, just not changing it, and then GDB won't stop. Often I don't want that though, particularly if I've got some kind of memory corruption problem. I really care about the raw memory, right? Not the expression. So with any, I think since GDB 9 or something, you can do watch-l or watch-location, which will just figure out where that expression resides in memory and watch that. rwatch, so if you remember rbreak, regular expression breakpoint, rwatch, something completely different, nothing at all to do with regular expressions. It's a read-only watch point. So there's another classic bit of GDB UI. We can also have awatch for an access watch point, which will stop whenever the memory is read or written, and of course not just when it's changed. Thread-specific watch points. Now in theory, unlike breakpoints, thread-specific watch points, if they're hardware watch points, will only need to stop when GDB will apply watch points to the individual threads. So you may, I haven't actually tested this, but you may find if GDB, at least if GDB is any good, the other threads will run kind of full speed unencumbered. So if you've got one thread that's hitting a watch point like loads of times, and you don't want to slow down by hitting that, thread-specific watch point should be nice and efficient, I think. And of course, we can have conditional watch points. And it's all part of the same namespace, right? So they all get watch points and breakpoints and catch points all get a number, and they all live in the same namespace, and you can delete and disable and enable them like that. We also have catch points, which are which kind of calls. They can catch various interesting things that might happen. System calls being a good example, but also C++ exceptions, both when they're thrown and when they're caught, and when they're rethrown, in fact. And I can catch things like fork and exec and other stuff. So catch points are kind of just stop when various interesting things happen. If I want to know what's available, tab complete is often your friend. So tab, and so you can see I can catch asserts and and exceptions. I think actually though exceptions is for Ada, so you probably don't want that. You probably want catch, throw, catch, or catch throw, or catch rethrow. Okay, I'm going to show a little demo now, kind of trying to wrap a bunch of this stuff together. How are we doing for time? I think we're okay. Right. So multiprocess debugging. So Chris talked before about, so maybe you've got some sort of distributed application, client server, whatever, and you want to debug multiple things at the same time. Well, I can just start 2 copies of GDB. Maybe I'll change the prompt on one of them at least to not completely confuse myself. Or maybe I want to control it all from the same GDB, which has various advantages. And let's look at how we might do that. So I'm going to do a similar thing that Chris did. Let's get a split window. Like that. All right. And now let me try and remember this demo. So we want to, I want to, do I want to say bash? Okay. You remember better than I do. Oh yeah, right. Thank you. Yeah, that's what I wanted to do. Complete brain frog. Right. So let's look at a program. This is just an arbitrary command, right? I wanted to debug some of that bit, make it a bit more interesting. Now let me get so we can see both these at the same time. Why doesn't that? Okay, you can detach this tab, I think. Detach current tab. There we go. So that's the PID of bash on the right-hand side. So let's just attach GDB to that. All right, so of course now if I type enter on the right-hand side, nothing happens. Bash is paused while we are debugging it. Okay? So I want to hook when I run that cat command, I want to hook that, and I'm going to do a multi-process debugging thing as well. So let's put a catch point on fork, and another catch point on exec. Now, notice I could have said catch syscall fork. That probably wouldn't quite do what I want, because on a modern Linux system, it's not really going to call fork. It's going to call clone, or probably clone 2, or maybe even clone 3. There are different types of fork. Catch fork will just put a catch point on all of the forky things. And the same with exec. You've got exec VE and all of that. So that's just so I can just go catch fork and catch exec. And let's run the program. So didn't expect that. Anyway, right. So let's just do that again. Cat hello.c. Right, so here we are. So I have, we've got a catch point on fork. Now, by default, with GDB, when the program being debugged forks, GDB will continue to trace the parent and allow the child just to run sort of, untraced. Now, I can change that, set follow fork mode, and I can set it to follow either the child or the parent. So I could change it to follow the child, but I don't want to follow just one or the other. I want to follow both. So what I'm going to do now is set detach on fork, which defaults to on, but if I set it to off, so let's look at our assembly code here. So we're just after the syscall for fork. So OX38 is probably the syscall number for, well, one of the forks. When we're actually inside the syscall, it's called a, you get two traps if you're doing ptrace syscall. You get a syscall entry stop and a syscall exit stop. So I think we'll be at a syscall entry stop. It hasn't done the fork yet, it's just about to. And if I do next I, to just next over that, run one instruction, now it should have done that fork. So if I look at what's in RAX, that looks like a PID. So I'm probably looking at the parent. And if I go info inferiors, yeah, look, we're debugging two things at the same time, two copies of bash at the same time. It's just done a fork. This works very like with threads, right? When you're debugging threads and you go info threads or you go thread 3, you just do the same with inferiors. So if I go inferior 2, well, it's just on a fork, so it looks awfully like, the two look awfully similar, don't they? But of course, RAX, which is the return value from the fork, is 0 in the child, because that's how fork works, right? So that's all good. So now I'm debugging both these things at the same time. If I continue the child, what I'll see, if I remember correctly, is everything's going to lock up if I just continue the child. Yeah, that's kind of depressing. So what's happened here is they've got, I think, locks are held. There's some kind of, there's something preventing that child from running. But if I go back to the parent, continue that, let's just see where we are. So that is inside the wait that follows the fork. So now it's waiting for its child. So now if I go back to inferior 2 and continue, well, now we hit the exec catch point. So look, we've exec'd cat here. I don't know why that doesn't select. Anyway, we've exec'd cat. So if I now continue from there, we should see cat runs to completion, info inferiors. So that inferior still exists, but it's not doing anything, like it's exited. And so I can go back to parent and continue. And okay, it's done another fork for some reason. I don't know why bash is running something else. So there we go. So multiple inferiors at the same time. I expect, in fact, no, I know, you can do this with remote debugging as well. So I might be using one GDB to control processes on different machines even at the same time. That's most of what we just covered, except there are other ways to add inferiors. The one that I showed how you probably want to do it, I think, which is by following fork. But maybe I want to attach to different processes at the same time. You can do that. I can just create an inferior by going and by add inferior, and then I can just attach just with the attach command to an arbitrary process, or indeed use remote debugging at that point. So add inferior kind of creates a kind of not shell. That's the wrong word to use, but a kind of null inferior that then I can populate by attaching it or whatever. Chris.
Yeah. So we're going to talk about threads now. By default in GDB, when you start it up and you've got multiple threads going, if you hit a breakpoint on any thread, all threads are stopped. And this is great if you want to see what's going on and see exactly the same, but that's not always what you want. So there's a concept of Nonstop mode, and if you set it on, what this means is only the thread that hit the breakpoint stops, the others continue running, and then you can start and continue -A, start them all if they're stopped. And since we're on threads, there's also things like thread apply to apply different commands. You can see threads 1 to 4, print the stack pointer, or do a backtrace. I'll do a very quick example of this, because I know we're getting a bit tight on time now. GDB threads. So we'll start. Okay. So here we have our threads. Basically, we're just going to launch 10 threads before create, and then sleep at 0. The threads aren't really doing much. They're just constantly while true, square rooting a random number. So it's not doing anything complex, but the main thread is going to stop at line 33 to sleep. So is that hopefully that feedback stopped. So the main thread is going to stop at line 33 to sleep. So let's just put a breakpoint on 33, and we can continue. And we see we spawn the threads. I'm not going to look at the code as much anymore, so let's use this trick again. So the win hides the source to 8, gives it a bit more space. So if I do info threads at this point, you can see they're all there. They're all basically stopped wherever they happen to be at that time. We can do the function which is also thread apply 1 to 3 p $PC. So we can print the program counter of the threads are stopped. But let's look at Nonstop mode as a comparison and see how things differ. So I have to kill this because you can't have any active inferiors when you change that. So set Nonstop on. At this point, info break points, we still have that breakpoint at 33. So the main thread is going to get to that one and stop. So I can just run this. So we run, start it up, launch our new thread, and thread 1 has hit that breakpoint. If I do info threads now, we can see the other threads are still running. This also means if I do that apply thread multiple, it can only apply to the stop thread. So the other threads are running, you can't print the program counter because it doesn't exist. That's not the state that those threads are in at that time. If I look at the source code, there's just enough to see. If we scroll up, we saw that while loop was doing while square round. So what I can do, just to bring those all to screeching halt, is put a breakpoint at line 17. And we'll see all the threads have hit that. So info threads. They're all stopped at the same place, as I expect. And at this point, that suddenly does work. So that's just very quickly multiple threads, how you can interact with them, and the non-stop mode, and ways of doing things. This allows you to tackle your multi-threaded application, whatever makes the most sense to you.
Particularly useful if you've got like other threads that might time out, that's doing some kind of heartbeat or some kind of application like that. Then stopping the threads in GDB can be a non-starter, but non-stop mode allows you to do that, and if you're really lucky, GDB Nonstop mode won't even crash. Your mileage may vary. Right, yeah, so calling inferior functions. So I'm sure many people have done this. Call foo, I can call the function foo. Often actually people do that to pretty print because they've got some pretty printer in their program they want to invoke. And they haven't been good people good past themselves and past selves, and they haven't got a Python pretty printer, so we call functions. That's quite a common use case. But you can do anything, right? And the function will just run and do whatever it runs. It might leave side effects. You can also just print the result of an expression, right? So I can go call foo, or I can print foo here, and the same thing, right? Because I've said you've got to run that function. If I've got C++ and I've got operator overloading, print foo plus bar might result in inferior functions being called. Print erno will result in an inferior function being called because erno is thread local and it runs a little bit of code to get the address of erno. And sometimes, although I think the very latest versions of GDB aren't so bad at this, but if you do something like this call strcpy, this actually is going to do, obviously it's going to do an inferior function call of strcpy, but it's also going to do an inferior function call of malloc to malloc some space for this literal string, and then copy that string in, and then run strcpy. So GDB sometimes can catch you out, and I speak from personal experience. If you happen to be debugging a custom malloc operation, that gets confusing. Right, how long do we have? No, there's never enough time, isn't there? But, right, time travel debugging. I'm going to do another quick poll. Who has heard of time travel debugging? Okay, and who's used it? Here's niche, you see. It will, I'm a bit biased, but this will change your lives. Right, so GDB has inbuilt time travel debugging, or sometimes it's called reverse debugging. That shell's being debugged, isn't it? I want to get rid of that. That's crashed.
New shell.
Yeah, nothing to see here.
Never happened.
Yeah, GDB didn't just ruin everything. I didn't need to shut that one down, did I? That was stupid. Right. Okay, time travel debugging. So time travel debugging is so useful, I think, because when you're debugging, you really want to know what happened. And the big limitation of most debuggers is they don't tell you what happened, they tell you what's happening. They tell you what's happening right now at this point you've stopped. You can do a backtrace and get some kind of historical what happened, but that's really limited, right? It's just a kind of sliver of your program's execution. We are meeting CPP. So I have here a program sort, which just basically gets some random data and sorts them using a bubble sort. And if I run it here, it doesn't print anything out, but it usually works. But I happen to know that there is a bug. So if we run this for long enough, it will segfault. Promise. Yeah, see? I never lie. Right. So let's load that up. Let's load the core file. Right. So there it is. So GDB. Okay. Backtrace. Not very much use. So that looks like some kind of stack smash. Of course, the core file just gives you this snapshot at the very end of the program execution. But I want to know what happened. I want to know how I got here. So I'm going to use GDB's inbuilt time travel debugging, which works. It is very slow, but this is a short program, so that's okay. So, and I'm going to do some other tricks as well. So start. So I'm going to put a breakpoint on main. I'm going to attach some commands to that breakpoint. So every time breakpoint 2 is hit, now it's going to issue these commands. First one is going to be enable recording, and then it's going to continue, and that's it. I'm going to put another breakpoint on exit. I'm going to attach some commands to that, which is just going to be to rerun the program. So if I get to exit without faulting, it's just going to rerun. I'm going to set confirmation off because otherwise it's going to ask me all the time whether I want to restart. Set pagination off because that's just annoying, and continue. So we're just running round and round. Every time it gets to the exit breakpoint, it's obviously run successfully without segfaulting, so it runs again, enables recording. You can see how slow this is, right? This runs in a blink of an eye normally. What GDB is doing is single step every single instruction and see what changed, but eventually it stopped because it's hit that segfault. Backtrace, still garbage, right? But here I can go reverse step I. So like a step I, like step instruction, but go back one, and look at that. Now I'm in where I would expect to be. So this is looking really like, stack corruption. Let's look at the stack pointer. Stack pointer is that. So if I look at, let's say, long star stack pointer, so that is the return address. Right, if I look at the, didn't mean to do that. I meant to do that. If I look at I'm at the ret instruction. Ret will pop the value that the stack pointer points to. It's a full descending stack, and that is the return address. And if I want to look at that memory, which I can do with the x command for examine, that memory doesn't exist. So, okay, that's kind of what I was expecting. But the question is, why did that happen? Right? Why does my stack contain garbage? Well, I'm going to do something that's super useful with time travel debugging, which is to set a watch point. Set a watch point, and then you run backwards. That will run backwards until the data changes, and that will tell me exactly who stomped on my stack. Now, there is a catch in later versions of GDB. Sadly, with its inbuilt time travel debugging, watch points seem to be broken, which is super sad because that's like probably the most useful, the killer feature of time travel debugging. But the good news is it's only hardware. We figured this out on the train, Chris and I, yesterday. It's only hardware watch points that are broken. So if I set can use hardware watch points to 0, now GDB will use software watch points. As I said earlier on, you don't want software watch points really because they're really slow, and GDB single steps and sees whether it's changed, and then it does another single step, and it just takes forever. But process record, which is what inbuilt GDB time travel debugging is called, does that anyway. That's how it works. So actually, software watch points are no problem, or at least no worse than hardware watch points. So let's just get back to the view I wanted. So now I'm going to set a watch point on the address. It's got to be location, that's what I was basically. It's got to be a location watch point, otherwise it's going to change the stack pointer every time. Long star stack pointer. Now, reverse continue will go back to when that location on the stack was written, which should have been when the function was called, right? Because it's supposed to be the return address, but we know it's not. Look at that. Who would have thought it? It's writing into the local array. Print I, it's writing into the 5th element of the array. And what is array? It's an array of only 32 elements, because if you look here, I've gone % size of array, and of course that's the size of the array in bytes, not elements. So, a whole bunch of stuff coming together there, show the power of time travel debugging. If you want time travel debugging that runs with decent performance, and you're doing more than a few thousand instructions, you want to look probably at either RR, which is an open source time travel debugger that's available, or there's some product from this company called Undo, which claims to do the same. It's really good.
I think we've got a couple of minutes left.
Yeah, so we've always more content than we've got time to do. Whole bunch of stuff. Maybe, as we've only got 2 minutes, we've got a few minutes. Any questions? We've got a bit more content we can run through, but there might be some questions. No question. Yes, question. Question is, if I have a GDB server, can I have several GDBs connecting to that GDB server at the same time? I don't know, but I'm going to guess no. I'd be very surprised. Yeah. But actually, I don't know. I'm not going to guess maybe. We'll try it afterwards. Maybe it would work. Yes, question.
So just to get it right, the difference between watch and watch-l is in watch we watch a symbol, and for watch-l we watch the address?
Yes. So the difference between watch-l and normal watch is, yeah, watch without the -l will watch the expression. And so, yeah, so if in my demo, if I'd forgotten to do watch-l, let's delete that watch point. Let's run to the end. Let's RSI. So if I go watch star like that, forgotten the -l, and then I reverse continue, it doesn't go very far. I reverse continue again, because the result of that expression, looking at the stack pointer, has changed because the stack pointer has changed. The kind of component inputs to that expression have changed, so the watch point triggers -l, but I wanted to look for that memory corruption, so I used -l. Actually, -l is just really a convenience thing. You can just take the address and then watch. You know, you can go, I can go watch star long star, and then just like paste in the hex address there, and that has the same effect. But watch -l is a bit more convenient. Except sometimes, and I haven't worked out when, sometimes it doesn't work. It just gives you an error that it can't do it, and in that case you can just watch what the address points to. Okay. Oh, no, there's lots of questions. Okay, yeah.
Small one. Can hardware watchpoint do expressions?
Can hardware watchpoints do expressions? Yes, GDB is quite smart at this. So if I've got an expression with multiple sort of component parts, it will put a hardware watchpoint on each of the bits of memory that combine to result in the evaluation of that expression. So if my expression is too complex, it'll run out of hardware watchpoints, and then it can't, and then it will probably fall back. It's kind of inconsistent here. So if I just try to set 5 regular hardware watchpoints, it sets them, and then when I continue the program, GDB says, I couldn't set all the hardware watchpoints, so I can't continue, so it's stopped. If it's trying to do a single watchpoint that it can't use the hardware watchpoints to construct, it then falls back to a software watchpoint like transparently. So yeah, it's a bit confusing. But yes, you can use hardware watchpoints on quite complex expressions, and it's kind of cool. Yeah, works pretty well. Yes?
For this thread specifier, can you use the named threads, like instead of thread 3? Can you use the name of the thread, like positive?
Can you use the name of the thread when you specify the thread? I don't think so. But we can try. We can try. Like, I've only got one thread here, but that's probably okay. So I can go thread name blah. So if I go thread blah, I don't think it will work. No, I think it has to be the numeric ID.
Yeah. So that's very useful for the actual programs. Like, they wouldn't be able to predict what the number would be.
That's a really good point. So how do you predict what the thread number is? Yeah, now you could write some Python to do this, I'm pretty sure. Yeah.
I think that's probably time.
Probably at time, maybe.
One last quick question, if there's one.
Any thoughts about LLDB?
It's a question of what about do you mean what about LLDB? Yeah.
I use GDB, but
Yeah. I don't know. What about it? I think it's fine. I mean, I just tend to use GDB. My experience, really nobody types LLDB. People use LLDB because it's what Xcode uses and some other stuff, but people tend to type GDB, and I think GDB it's just richer. There's more, I think some of these features, like LLDB I think now has the Python, and it has a bunch of this stuff, but, and it has some stuff that GDB doesn't, so they're just kind of different tools for the same job, I guess. But I can't do a talk on LLDB because I don't use it. All right, we better stop there because we outstayed our welcome, but thank you very much, everybody.